Our second speaker is Stephen Wallander. Please welcome Stephen. Stephen will be presenting on the slipping effects of managed aquifer recharge within agricultural lands, evidences from a landscape level model. Thank you.
Great. Thank you. So I'm an economist with the United States Department of Agriculture, and I will be presenting a research project we have with the University of Arkansas, and my colleagues Dot Tron and Kent Kovac, also economists. And so I guess you know you're in trouble when the economists show up at your conferences, right? But we'll be looking at the behavioral response using a simulation model of what it might look like in the future under managed aquifer recharge and how that interacts with drought risk. The basic research question is what happens to the recharged groundwater given the choices that farmers, that irrigators are able to make as the aquifer conditions changed. And that really splits into two questions. One, what portion of the recharged groundwater leads to recovery of groundwater levels? We're in an aquifer here where there's severe overdraft. And what portion results in what we are calling slippage? And slippage is defined as an increase in groundwater pumping relative to a no recharge scenario. So if there's zero slippage, if all of the water you're recharging is trying to raise the groundwater levels back to something like their historical level, then you're not getting any other use out of it other than lowering future pumping costs. Alternatively, if, sort of as the example we just heard, if you're using most of that water in the near term and you're keeping the groundwater levels approximately where they are, then you have a lot of slippage. So slippage is an economic benefit, it's just a different one than is sometimes conceived of. To put our project in context, this is what the irrigation regions in the United States look like. What we've done here is we've clipped the land to only show cropland and to only show counties where at least 10% of cropland is irrigated. And on the color ramp, the counties that are red have at least 75% of the cropland irrigated. So obviously in the arid western United States, you have nearly 100% irrigation in most of the counties when we're talking about cropland. But you also have something close to that in the southern Mississippi, the area we'll be looking at on the Mississippi embayment or the Mississippi alluvial aquifer. The Mississippi embayment is one of the three major aquifers in terms of scale in the United States. Together, the Central Valley, the High Plains, and the Mississippi system account for about 70% of total groundwater irrigation in the U.S., and all three of those systems have severe overdraft problems, at least in localized areas. The Mississippi system is overdrafted by about 150 million acre feet relative to pre-development levels, or about 22% total depletion. We'll be focusing on an area in Arkansas that is where the most severe overdraft in that aquifer occurs. It's 11 different counties and predominantly agricultural. We have a hydroeconomic model that is going to dynamically optimize irrigation water use and land allocation to different irrigated crops and to irrigated and non-irrigated land. And it's also going to be optimizing groundwater recharge locations and quantity, that should say quantity. And so it's going to choose where within the system to do the recharge under different parameters. We'll run the model for 120 years to look at the evolution of the system. And for recharge, we'll be using well injection. The main reason for using that here is that you have a lot of pumping out of the alluvial aquifer, but you have a clay layer about 10 feet thick overlaying that in most areas, and so building recharge basins is extremely expensive. The hydrologic model has 2,000 grid cells, and for our baseline land use, we're using an estimate from 2017 satellite data of what crop is growing in each one of those cells. In addition to the MAR, farms have the opportunity to take the excess winter flows and use on-farm storage instead of recharge. And we have reservoir storage costs coming from a Mayora tool that was used in the recent past to do some research on looking at storage simulations. The MAR methods are coming from a United States Geological Survey pilot study where they found a range of recharge in wells from about 155 to 700 acre-feet per year. And then for drought, when we're looking at how frequently the drought's occurring, we'll be using the Palmer Drought Severity Index. The core of this model is really the land use choice. That's what's driving a lot of the predictions about what would happen. It's a dynamic partial equilibrium allocation of cropland. On the irrigated side, farmers can allocate the land to rice, corn, soybeans, or cotton. They can also grow dryland soybeans, or they can grow double crop soybeans and winter wheat. And that constitutes pretty much almost everything that's grown in that area right now. They can also change their irrigation technology. For rice, they can change it from the traditional flooding system to a laser leveled system. For the others, crops, they can change it from traditional furrow irrigation to a more improved gravity system using polypipe and gates and other things. They can also engage in land fallowing. So during a drought or as groundwater levels get pumped down too far, they may irrigate in alternate years and grow the dryland crop options or not grow at all for some years. And they're really using the winter precipitation. And so one study looking at sort of how much additional water is available in this system for recharge looked at two of the rivers that are tributary to the Mississippi, the Arkansas and the White, and estimated that you could get as much as 5.5 million acre-feet, so almost 7 cubic kilometers of recharge per year, if you could figure out how to detain, store, and transfer that water to recharge sites. So there's plenty of water available for recharge. The real question is the cost of capturing it and moving it and recharging it. And as I mentioned, what we'd be looking at is two things that you could do with that water, either the injection recharge or the on-farm reservoir storage. And so this, similar to what we heard before, this is capturing your winter flows and trying to make those available for, in the case of on-farm storage, primarily for the following spring and summer crops, and in the case of recharge for future years. The real question here that we have to run this model and look at the sensitivity tests is how much is the water going to cost? The idea is that the irrigators are going to need to bear the capital cost of whatever the system is used to ultimately get the water out of the Arkansas and the White Rivers, but there's a lot of uncertainty about how those capital costs are going to get passed along and what it's going to be. So we look at a range of values from $10 per acre foot to $100 per acre foot, basically to acquire the water in order to pay the capital costs of the storage, in addition to the variable transfer pumping costs from the river to whatever the recharge site is. So that additional cost varies by your recharge site. For the drought frequency, we also want to look at how the returns and the decisions vary depending on the drought, and that's really going to, we start with our historical record of drought, but we think we're probably entering an era where we're going to have increased frequency of drought, and so we run the 120 years under both baseline frequency and increased drought frequency. So these are the main results in terms of how much recharge the model predicts. The chart on the left is your baseline drought. The chart on the right, which looks pretty similar, is your increased frequency drought. And the first thing I'll draw your attention to are the two lines, the two red lines that start high and move low. That's the $20 per acre foot scenario. And you're getting about 450 to 500,000 acre feet per year of recharge initially. And then that's going down over time. So when the water's cheap, what the model's predicting is that you'll start with high amounts of recharge in the initial time periods, and then as your groundwater levels recover, the marginal benefits of doing recharge will go down, and you'll recharge less and less over time until the aquifer really recovers back to much higher elevations. For the other, as soon as you move up to $40 per acre foot, that story changes dramatically. You start low because the water's so expensive, and as the aquifer continues to decline over time, you're not recharging enough to reverse that scenario. The marginal benefits of recharge go up, and you start to get more recharge over time. So that's the green lines. And then as you move to $60 or $80 an acre foot for the water that you're supplying, they look similar to the $40 per acre foot, but you're recharging a lot less. So this just restates how I was explaining what those charts are showing. A lot of what's driving that is this reaction to the water that's being recharged. And so when you're getting a lot of recharge initially at the $20 per acre foot, you're getting an increase in the blue bar, which is your irrigated rice, and you're also getting a pretty significant increase in your irrigated soybeans and cotton, which is the green bar. And the decline you're seeing is a reduction in the area of non-irrigated crops and fallow. And so by putting more water into the aquifer, you're getting a lot more irrigated production. You get a similar effect, but it's smaller with the lower amounts of recharge in the other scenarios. You can look at what that means in terms of the economic benefits to farms in the area. When you have a low-cost supply of water for recharge, you're getting an increase in profits of about 1.5 to 2 percentage points over that 120 years. It's a slightly bigger economic benefit when you're facing more drought, which is not so surprising. You're reducing the constraint of drought a little bit. When you get more expensive water, you're doing less recharge, you're getting much less of an economic benefit, but it still is a positive one. So that brings me to the slippage results, sort of these two pieces, the acreage piece and the recharge piece coming together. At the low-cost scenario with $20 per acre foot, about 70% of the recharged water is remaining in the aquifer and raising that groundwater level, and about 30% of it is getting used through that expansion in irrigated production. That basically flips when you get to the other scenarios where you have more expensive water. Only about 30% of the water is remaining in the aquifer, and about 70% of it is going to that slippage or that increased irrigated production. Drought changes this, but only by a little bit. It increases the slippage, the amount of irrigated production that you get in response to MAR by about 1 to 3 percentage points. So that's the conclusion of that slide. Thank you.
I'm so happy that I have a very little work, because in principle I should show these to the ones are a long speech. But so thank you very much for being on time.
You're welcome.
Thank you, Stephen. Congratulations. Any questions? Yes, please. We have a microphone coming. And you can repeat the question,
Okay.
Stephen.
Take the microphone.
What are the key assumptions that went into this hydroeconomic modeling, which is very, very intriguing, because we don't get the cost and benefits right, nothing will really grow.
Okay. So the question was about the assumptions that are going into using a 120-year time frame. When you're dealing with a region like this size in terms of the economic assumptions, for the most part, you're taking your baseline assumptions in terms of prices and demand for the commodities, and we hold those constant. We have, I believe, the underlying sort of weather and climate scenario. I believe that the taking for this is sort of a GCM average over that time, or run with a historical 120-year scenario. And so most everything else you're holding as the constant, and the main thing you're interested in varying is the hydrologic conditions in response to the recharge.
Okay, thank you.
Yeah, you mentioned something about water application rates. What do you mean? Did you incorporate a water production function in the model or what?
The water application rates for the crops are based on the crop water requirements, basically calibrated to historical application rates. So the crop choice determines the amount of water that gets applied, but it interacts with, the amount of water they apply interacts with the irrigation technology choice. So if they move to a more efficient system, they can apply a little bit less. And it also interacts with the drought, the draws of what the drought you have in each year. So the drought for soybeans increases the crop water requirement by about 1 to 2 inches, and it increases the crop water requirement for rice by about 5 to 10 inches.
Testing my long-distance vision, but I think it's our good friend Peter Dillon up the back.
Hi, Steve. Thank you very much for your interesting talk. Steve, I'm really surprised that you're showing benefits, actually, or benefits exceeding costs. I'm not sure whether, perhaps I'm not understanding it properly, but it seemed that even at $60 an acre foot, that seems a very low price for a well injection system with natural waters. And rice and wheat are low-valued crops. So, I mean, just intuitively, I would say that seems a really unlikely scenario to play out, that your managed aquifer recharge would be of value if you're just looking at it from in terms of crop returns. If you're looking at fixed-rooted crops, where your drought is very significant, because if you kill your tree, then you've lost production for a number of years, then you can afford to invest more in increasing the security of the supply.
Right.
So maybe I've got the wrong end of I've got the problem by the tail rather than looking at it the way that it should be looked at.
Well, the reason we have positive returns is essentially it's a model that's optimizing recharge. So it won't put recharge on any sites unless there's a net benefit to recharge at those sites. It's sort of a social planner model. And the baseline case is you don't build any system to pull water out of the rivers. So you've got, in your baseline case, you have a constraint in that there's no additional water made available. And then each of the runs, you're relaxing that constraint a little bit and saying either there's really cheap water available at $10 or $20 an acre foot, or it's more expensive at 40 or 60 or 80. But in all of those cases, because you're relaxing a constraint, you're going to get some, even if it's minimal, net positive benefit. So once you get up to 60, I mean, you're talking around a 0.1, 0.2 percentage point increase in net returns. It's not very big. And then the question becomes, are the cost assumptions about capturing the water, recharging the water, are those valid? Because those are the key assumptions that go into the model to say that there is some economic benefit.
We'll take one more. Thank you.
Thank you. My name is Tim Parker, and I'm from Sacramento, California. And yeah, I think, as I recall, you mentioned assumption of well injection. And I think maybe for the economics of the crops, that would be very expensive, and that's part of the issue. That really only recharge with infiltration at the surface is going to be, at least from our experience in California, is going to be not going to be cost prohibitive, and maybe that's something to look at. The other thing is, as Peter mentioned, the permanent crops, things like pistachios, walnuts, grapes, more high-value crops are more useful for considering those more expensive technologies. So. I've really appreciated your presentation, though, and look forward to following up with you, because economics is such a key role in the whole situation.
Yeah. Thank you. And just the one thing I might say in response to that, we would like to extend the model to look at either infiltration basins, on-field flooding, or using what canals do exist to do recharge. The challenge for us modeling that right now is that the existing data doesn't really let you spatially differentiate between areas where you might have a thin enough confining layer that a basin would make sense. There are a couple of data collection efforts that are in the works that are hopefully going to open up that modeling avenue in the next few years that would let us think more about where those might go spatially given the substrate characteristics.
Stephen, we need all disciplines involved in managed aquifer recharge and integrated water resource management, and economists are always welcome. Thank you very much.
Thank you.